Space travel has always captivated the human imagination. We dream of exploring distant planets and unraveling the mysteries of the cosmos. To venture further into the cosmos, we need revolutionary propulsion systems. Plasma propulsion is one such technology that promises to revolutionize space travel. By harnessing the power of plasma, these engines can propel spacecraft farther and faster than ever before, opening up new frontiers in space exploration. Traditional chemical rockets have limitations in terms of fuel efficiency and thrust. Plasma propulsion offers a more efficient and sustainable alternative. Imagine a future where spacecraft could travel at incredible speeds, allowing us to reach destinations like Mars in a fraction of the time it takes today. This is the promise of plasma propulsion, and the reason it is considered a game-changer for space exploration. To understand plasma propulsion, we first need to understand plasma itself. We are familiar with three states of matter: solid, liquid, and gas. Plasma is often called the fourth state of matter. When a gas is heated to extremely high temperatures, its atoms lose some or all of their electrons, creating a mixture of ions and electrons. This ionized gas is called plasma. Plasma is found throughout the universe in stars, nebulae, and lightning. In the heart of the sun, for example, hydrogen atoms are stripped of their electrons, forming a plasma that undergoes nuclear fusion, releasing tremendous energy. Scientists and engineers are working to harness the power of plasma here on Earth, and plasma propulsion is one of the most promising applications. Plasma propulsion engines generate thrust by using magnetic fields to accelerate and expel plasma. While the specifics vary depending on the type of engine, the fundamental principle remains the same. Create a plasma, heat it to extremely high temperatures, and then expel it at high speed to generate thrust. This is similar to how a jet engine works, but instead of burning fuel with oxygen, a plasma engine uses electricity to heat and accelerate the plasma. The process begins by injecting a propellant gas, typically xenon or krypton, into a chamber. This gas is then ionized, stripped of its electrons, creating the plasma. Powerful magnets surrounding the chamber create a magnetic field that confines and accelerates the plasma, heating it to millions of degrees. This superheated plasma is then expelled through a nozzle at high speed, generating thrust. One of the biggest advantages of plasma propulsion over traditional chemical rockets is its efficiency. Chemical rockets are powerful, but they are also very inefficient. They have to carry a lot of heavy fuel and they burn it up very quickly. This limits how far and fast they can travel, especially for long-duration missions. Plasma propulsion, on the other hand, uses much less propellant to produce the same amount of thrust. This is because plasma engines can achieve much higher exhaust velocities than chemical rockets. The higher the exhaust velocity, the more efficiently a spacecraft can accelerate, allowing it to travel farther on the same amount of fuel. Section 5. Types of plasma engines, a spectrum of innovation. There are several different types of plasma propulsion engines, each with its own strengths and weaknesses. Some of the most common types include Hall effect thrusters, or HETs, use a magnetic field to confine and accelerate the plasma, creating thrust. They are relatively simple, reliable, and have been used successfully on several space missions. Ion thrusters use an electric field to accelerate ions, which are atoms that have lost or gained electrons. They are very efficient but produce very low thrust, making them suitable for long-duration missions where a small but constant acceleration is desired. Magnetoplasma dynamic thrusters, or MPDTs, use a combination of electric and magnetic fields to accelerate plasma to very high speeds. They have the potential to produce very high thrust but are still in the experimental stage. Each type of plasma engine has its own advantages and disadvantages, making them suitable for different types of missions. As research and development continue, we can expect to see even more advanced and efficient plasma propulsion systems in the future. Section 6. Current applications: plasma engines in action. Plasma propulsion is not just a futuristic concept, it is a reality. Plasma engines have already been used successfully on several space missions. For example, NASA's Deep Space One spacecraft, launched in 1998, used an ion thruster for its primary propulsion system. The mission demonstrated the feasibility of ion propulsion for interplanetary travel, paving the way for future missions. More recently, NASA's Dawn spacecraft, launched in 2007, used ion thrusters to journey to and orbit the asteroid Vesta and the dwarf planet Ceres. This mission showcased the ability of ion propulsion to enable complex maneuvers and long-duration observations in the asteroid belt. These successful missions have proven the viability of plasma propulsion for space exploration and paved the way for more ambitious endeavors. Section 7: Future Frontiers, Deep Space Exploration and Beyond. The future of space exploration is closely tied to the development of advanced propulsion systems like plasma engines. Their potential applications extend far beyond our current capabilities, enabling missions that were once considered science fiction. Here are just a few examples of how plasma propulsion could shape the future of space travel. Human missions to Mars. Plasma propulsion could significantly reduce the travel time to Mars, making human missions to the Red Planet more feasible. This would be a game-changer for human space exploration, opening up a new frontier for scientific discovery and human ingenuity. Exploring the outer solar system. The outer solar system, with its gas giants, icy moons, and dwarf planets, holds many mysteries waiting to be explored. Plasma propulsion could allow us to send spacecraft on long-duration missions to these distant worlds, providing us with invaluable data and insights. Interstellar travel. While still in the realm of science fiction, interstellar travel, or travel to other star systems, might one day become possible with advanced plasma propulsion systems. These engines could potentially accelerate spacecraft to a significant fraction of the speed of light, making interstellar journeys conceivable within a human lifetime. These are just a few of the exciting possibilities that plasma propulsion could unlock. As we continue to develop and refine this technology, we can expect to see even more ambitious and groundbreaking space missions in the years to come. Section 8. Conclusion. A universe of possibilities. Plasma propulsion represents a pivotal step forward in our quest to explore the cosmos. By harnessing the power of plasma, we can overcome the limitations of traditional chemical rockets and unlock new possibilities for space travel. As we continue to develop and refine this technology, we can expect to see plasma engines playing an increasingly important role in space exploration, enabling us to reach farther, faster, and explore the universe as never before. The future of space travel is bright, powered by the promise of plasma propulsion and the boundless curiosity of the human spirit.